field are normally distributed, and that the standard deviation of his tomatoes in the past is 40 grams, use the sample mean to create a 99% confidence interval for the population mean. So for communicate, the first thing we have to do is establish our parameter mu. So mu is equal to the mean weight of all tomatoes in his field. Then we know that the C percent is 99%, okay, which tells us that our Z star value is 2.576. Remember, we can calculate that on Desmos using a normal distribution. We know our sample size is 4, X bar is 110, and sigma is 40. Okay, then we move on to our conditions. So checking our conditions, first random. Okay, this was a random sample, so we're good. Okay, independent, we check the 10% condition. So 4 is less than or equal to 10% of all tomatoes. Again, safe assumption. And then for normal, we use central limit theorem. And if our sample size is smaller than 30, we need to either hope that the problem talked about the population being normally distributed, or we would have to graph if given data. Well, since we're not given any data, like a table of data, and the problem, if we look back, does state that assuming the population of all tomatoes in his field are normally distributed. So since the population is normal, this implies that the sampling distribution is approximately normal. For calculate, we would use a one sample Z interval for means. Okay. And this would give us 58.48, 161.52. So to show you that on Desmos, we are going to go to add an inference, and then we're doing a Z-test. Okay, we're going to go to stats, and we're going to type in all the information that we have. So our sample size was 4, our mean was 110, and our population standard deviation is 40. I hit create test. We're doing a confidence interval, and this is for 99% confident, so 0.99. And then notice I got 58.48 and 161.5, and if I click here, it would actually see that this is 161.517, which rounds to 5.2. Okay, now we have our conclusion. So we say we are 99% confident that the true mean weight of tomatoes will be between 58.48 grams and 161.52 grams. Notice that since I had units attached to this problem, I know in my conclusion I have to attach those units back to my answer. So it said, notice that since in this problem we knew standard deviation, okay, this is a type of problem that I would describe as a unicorn problem. Okay, you're typically not going to see this type of problem because typically the standard deviation is not known. Okay, when the standard deviation is not known, we have to use the test statistic T star using a T distribution in order to approximate Z star or approximate our standard deviation when it's not known. So it says the T distribution is a family of related distribution which depend on a parameter called degrees of freedom. Degrees of freedom is denoted as df and is easy to calculate because the formula is just degrees of freedom is sample size minus 1, so n minus 1. What's important to define as a t-distribution is that they are unimodal, symmetric, and bell-shaped, just like a normal distribution. However, t-distributions with only a few degrees of freedom, which means very small degrees of freedom, have longer tails and larger standard deviation than normal. So thinking about the relationship of the two. Okay, so now we're gonna dive more into that relationship and learn how to actually find that t-star value. So it says the tails on a t-distribution are fatter than a standard normal distribution. So tails are fatter. This is true because the smaller our sample size, the more variation we have, which means we have fatter tails. The larger our sample size, which means we have a larger degrees of freedom, the closer the t-distribution will get towards the standard normal distribution. So looking at this diagram here, we have our standard normal that I'm just going to highlight in blue. And then I'm just going to go ahead and highlight the t-distribution where degrees of freedom is 4. Okay. And so if you look at the tails, remember these are the tails, they say that the tails are fatter, and they mean that the distance between the axis and the end of the tail is greater. That's what they mean by fatter. There's more distance here compared to that tiny distance of the standard normal distribution. And as our degrees of freedom increase, so notice how this degrees of freedom is 20. If we actually trace this one, you'll notice that it's getting closer to the tails of the normal standard distribution, and the center is almost the same. Okay. Now it says calculating t-star. So remember, we are not using a calculator. Instead, we are using Desmos. So that means we don't need any of this right here. So I'm just going to cross all that out. Okay. We are going to actually be using Desmos, and on Desmos we're going to be using a t-distribution. So the steps here would be to go to inference, okay, go to t-distribution, which is underneath probability distributions. We have to remember that our degrees of freedom is n minus 1, so we'll have to know our sample size. We're going to click on bounds and right for the region, and then we are going to type the area of one tail. Okay, so we'll see that more in action on the examples. Okay. So for example, it says find t-star for the following situations. 90% confidence interval with n equal to 5. Well, first I'm going to establish my t-star value. So this is negative t-star, this is positive t-star, okay, which means this area in between is representing a 90% confidence interval. So if this entire area is supposed to equal 100%, that means that each of the tails, since it's symmetric, are going to have to be the same. So that means we have 90 minus 10, or sorry, 100 minus 90, which is 10. So that's representing the area of both tails. Take that area, divide it by 2, and we get 5, which means I have 5% area on either side of the tails. So I'm going to use my n equal to 5. I'm going to calculate my degrees of freedom, which is 5 minus 1. That gives me 4. Okay, my area is just going to be one of the tails, and since I found it to be 5%, this is 0.05 as a decimal. And then I'm going to use that information to find t-star. So again, go to Desmos. On Desmos, I'm going to go to add an inference, click on probability distribution, go to t-distribution, type in my degrees of freedom is 4, and I don't change anything else. The shift and scale, just leave it alone. Hit create distribution, hit the drop down, make sure I'm in the right region, I'm on the bounds for compute, and then in that spot after the equal sign, I'm putting the area of one tail. So that is 0.05, and I get my T star value of 2.132. Okay, so T star is equal to 2.132. Okay, so you're going to do the same for the rest of them. So I would go ahead and pause the video. Okay, go back and practice with the next three, and then unpause it when you want to check your answers. Okay, so what I'm going to do is I'm just going to be setting up the rest of them so you can go back and check your answers later. Remember, you find these T star values by using Desmos. And the biggest mistake that can happen here is that you don't convert your percents into decimals, or you don't convert them correctly. So for example, this was 2.5%. 2.5% as a decimal is 0.025. And then for this one, the area of each of the tails are 0.5%, so we would have to turn that into a decimal, and that's 0.005 as a decimal. And we would get the T star value 2.724. Okay. So now we're going to look at how to calculate a confidence interval for a mean with an unknown standard deviation. So this one is more typical. It says when conditions are met, a C% confidence interval for an unknown proportion mu is the following: x bar plus or minus T star times S divided by the square root of n, where T star is the critical value for a T distribution with C% of its area between negative T star and T star. This inference is called a one sample T interval for mean. Okay, so looking at the conditions for that, notice our conditions are still random, independent, and normal. So for random, remember we need random selection, okay, or random assignment. For independence, we check the 10% condition, so the sample size has to be less than or equal to 10% of the population size. We do not check independence for experiments. And then for normality, we use the central limit theorem that states that n has to be greater than or equal to 30. Okay, if n is less than 30, we either check back in the problem and see if the original population is normally distributed, or we have to graph the sample data to make sure that there are no outliers and no extreme skewness. So looking at an example, it says you recently read an article that said averaging 30 minutes of exercise a week will help fend off cancer. A random sample of 10 U.S. adults was taken, and they were asked how many minutes of exercise each week they got. The data is given below. Construct a 95% confidence interval to estimate the true population mean. Based on the confidence interval, do you believe that adults are exercising enough to ward off cancer? Explain. Okay, so we're going to be using our 4 C's in this FRQ. So first, the communicate. We're going to write all the information that we already know. Okay, so first we establish our parameter. So mu is equal to the average minutes of exercise in a week. We know our sample size is 10. X bar, okay, we have to find X bar. S, our standard deviation, we're going to need to find that. Our degrees of freedom is 10 minus 1, which is 9. And then since we're doing a 95% confidence interval, if we go back and calculate T star like we just did previously, we would find that T star is 2.262. Okay. So in order to continue this, we actually have to go to Desmos and create a list and then find mean and standard deviation. So again, this is mean and this is standard deviation. Okay, so going back to Desmos, I'm going to go ahead and exit out of that, and I'm going to create a list. So I'm going to go ahead and label this list L. So L is equal to bracket, and then I'm going to type in my list from the problem. So 265, 274, 281, 289, 304, 243, 275, 290, 325, and 286. And I should have 10 elements in my list. So on the next line, I'm going to go ahead and go to Functions, click on Mean, and then put L for my list. So on my X bar, I'm going to write 283.2. Okay, then I'm going to go back and I'm going to go to Functions, click on Standard Deviation, put in my list for L, and I'm going to write 22.04 on my communication section of my FRQ. So going back to the FRQ, I'm going to fill in those answers that I got, so 283.2 and 22.04. Okay, now I'm going to move on to my conditions. So first I'm going to check my random condition. And in the problem, remember they said a random sample was taken. So random sample. Okay, then I'm going to check independence by using the 10% condition. My sample size is 10, so 10 is less than or equal to 10% of the population, which is all adults who exercise. And then lastly, for normal, I'm going to attempt to use CLT, but since 10 is less than 30, we have to graph. And typically what we're graphing is going to be a histogram. Okay, that's just the easiest to be able to see outliers and extreme skewness. So from here, I'm going to actually go back to Desmos. Okay. Using my list, I'm going to go to Functions, Visualizations, and click on Histogram, and I'm going to type in my list here. Okay, I'm going to make sure that my bar height is set to count and my bin alignment is to the left, and then I'm going to hit that magnifying glass to recenter it. Notice that at this point here, okay, even though this is a histogram, I have way too many bars, or sorry, way too many bins. I should have 5 to 6 bins. And also, I have a bunch of gaps here that are telling me I might have a bunch of outliers. Well, one thing to fix this is I need to calculate the bin width. And the bin width is going to be the range divided by the square root of n. So our range is going to be our maximum value minus our minimum value. So my maximum value is 325, so 325. Minus my minimum value, which is 243. Okay, and then I'm going to divide that by the square root of n, and n is my sample size, which is 10. And notice I get the number 25.93. That means when I do my bin width, I'm going to check the numbers 25, recenter that with the magnifying glass, and then I'm going to check the number 26, okay? So notice when I'm on 26, I only have 4 bins, but when I go to 25, I have 5 bins. And remember, the idea behind this is I should have 5 or 6 bins. So now that I have that, I'm going to go back to my FRQ, and I'm going to draw a sketch of that histogram. Okay, before I do that, let me remind you that bin width, okay, is the range divided by the square root of n, okay? If you get a decimal, go ahead and choose the whole number surrounding it. So in our example, we chose 25 and 26, and we want to have 5 or 6 bins. Okay, so when I draw my histogram, I need to make sure I label everything. So this is minutes per week, and this is my frequency. And then I'm gonna label this up to 4. So 1, 2, 3, 4. And then this starting at 240, I'm gonna go by 20s until I hit 340. So I have 260, 280, 300, 320. And then I'm gonna create my bins. Okay. Okay, and then I'm gonna just make sure I outline them so you can clearly see them, because with the highlighter, as I was highlighting, it kind of just got all mixed together. So now that I have my histogram laid out, it's labeled, and I have the scale on both the axes. I'm then looking at this to see if I have any outliers or extreme skewness. So remember, an outlier on a histogram means I'm going to have a large gap in my data. Since I don't see a large gap in my data, I'm going to say there are no visual outliers. And then I'm going to check for extreme skewness. So remember, skewness means majority of my data is either to the left or to the right. Okay, I'm looking for extreme skewness. So if I don't see anything extreme, then I can say that this is okay. So there are no visual outliers or extreme skewness. So this implies that the sampling distribution is approximately normal, and that's what we were trying to prove. Okay, now going on to the next C, which is calculate. I first have to name my inference, and my name of my inference is a one sample, because I only have one sample. T, because I'm using a T distribution. Interval, because I'm doing a confidence interval. For means, because that's my parameter. Okay, so I would go on to Desmos to find this answer. Okay, on a new line, I'm going to go to add an inference, and I'm going to click on t-test instead of z-test, because I'm using a T distribution. So t-test, and on t-test, I have to put my data. Well, I already labeled all my data L, so I'm going to just put L. Create test, and then I'm doing a confidence interval that's 95% confident, so I'm going to put 0.95, and I get the interval of 267.4 to 299. So that's my answer. Say so 267.4 and 299. So then I take my answer and I complete my last C, which is my conclusion. And I say that we are 95% confident that the true average time adults spend exercising per week is between 267.4 minutes and 299 minutes. Okay. Remember, we had one more question up there, and that question was saying based Based on this confidence interval, do you believe that adults are exercising enough to ward off cancer? Well, the study said in order to ward off cancer, we have to be averaging 300 minutes. So if I look at my interval, notice that this is 267 to 299. The number 300 is not inside of that interval, which means I don't believe that adults are exercising enough to ward off cancer. So I'm going to add that to my conclusion. So I'm going to say, sorry. Sorry, excuse me. Okay, sorry, excuse me. I'm going to say that since our interval doesn't contain 300 minutes, I do not believe adults are exercising enough to ward off cancer. And again, this last sentence here is answering that second part of the question.